La diffusion vient de démarrer. Tous les participants sont en mode écoute seule.
Hello everyone, my name is Rachel Collins and I'm one of Physics World's webinar moderators. I'd like to welcome you to the penultimate day of Quantum Week and to today's webinar, A Roadmap for the Quantum Internet. So thank you for joining us, and thank you also to the sponsors of today's event, Institute of Physics Publishing. Before we get started, there's a few bits of housekeeping relating to how to participate in the webinar. You will have joined the presentation listening using your camera's speaker system by default. However, if you would prefer to join using a telephone, select telephone in the audio pane of the control panel, and the dial-in information will be displayed. You can submit text questions to today's presenters by typing them into the questions pane of your control panel. And if you have any technical difficulties during the webinar, please type these into the chat function and my colleague will help you. Today's webinar will be presented by Tracy Northup, the Ingeborg Hochmer Professor of Experimental Physics at the University of Innsbruck in Austria, and Harold Ollivier, Head of the Quantum Technologies Programme at INRIA. They will be answering such questions as: what is the quantum internet? Why does it exist? When will it arrive? What new capabilities will the quantum internet enable, considering quantum hardware, interfaces, software, simulations, and applications? So both our speakers welcome your questions as part of this webinar, so do send them in at any time during their presentation using that questions facility in the control panel. We will pose them, as many as we have time for, in the Q&A session at the end of their presentation, and any that go unanswered will be answered by email once the webinar is over. So I will now hand over to our speakers.
Rachel, thank you so much. So Harold and I are both delighted to be able to talk here today about a roadmap for the quantum internet. And first, I wanted to briefly explain the context for the presentation. So Harold and I are both part of a consortium in Europe that's known as the Quantum Internet Alliance. And this is made up, on the one hand, of industry partners who are focusing on engineering components for quantum internet, and you see several of them here, as well as superconnecting facilities for blueprint simulations, and then an institution focused on bridging research to applied technology. We're also very interested in engaging with the classical internet community and with working with companies like SAP and VeriCloud to examine real world use cases. And then the basic scientific research in this project is being done at a number of universities. So I'm at the University of Innsbruck, and Harold was at CNRS. He's now at INRIA, the French National Research Institute, was focused on computer science engineering. And then we have also some partners, Network Operator Perspective and Fibers. They also offer a connection to the industry for quantum key distribution and then end user perspectives. These are partners who aren't directly financed by this consortium, but who are able to kind of contribute and participate in meetings and discussions. So yeah, as you can see, this represents now a number of different university partners as well as representatives of industry kind of coming together from a number of different backgrounds. And so then the problem that we want to address is, how could we work together to construct a quantum internet? And then to start off with that, we should think about why one would want to do such a thing, and I'll turn over to Harold to take a look at that.
Thanks, Tracy, and hi, everyone. Yeah, I think it's a good idea to just start by asking a bold question, like why a quantum internet? Well, obviously, you've seen the list of institutions and the partners in the consortium, and everyone in there is really convinced that quantum technologies, quantum computers, communication, and devices like sensors will have a profound impact on our society in the future. And but at the same time, we realized that unlike the technologies that we are using and we are accustomed to, these quantum technologies are not linked to one another. In fact, today, when we are using a classical computer, we don't even think about connecting it to the internet, to other computers, to other facilities to perform complicated tasks, such as collaborative tasks, offloading high computation load to huge servers or data centers. Same for the memories. And unlike these technologies, quantum technologies are not linked together automatically. You have to build something to link them together and to actually, and that's we think here, really unlock the power of these quantum technologies by making them available on a much broader scale and much touching people much more widely than just having a quantum computer sitting in a data center and able to only manipulate quantum information locally. What we want is that these quantum computers, in the same way classical computers do, are able to share their data and collaborate on difficult problems together. So that's the idea of a quantum internet. Maybe you might ask, well, why should we think about the quantum internet now? Well, actually, some of the members of the consortiums are already interested in these kind of questions for the following reason. When people are starting, end users are starting to use quantum computing facilities, even the primitive ones that we are able to have now, they do that over classical communication, and they access these quantum computers remotely, so they delegate the computation. And the question here is how much trust do you have into these quantum computers executing your computation correctly, and how private is these data that you send to these quantum computers? And the question is not easy to answer, and in fact, part of the motivation for building a quantum internet is to secure this kind of situations where you have a user of a quantum computing facility remotely accessing the quantum computer and wanting to protect its data, its computation, the IP of the algorithm is using, and of course the results. And this is an actual question. It's not a question for the future. It's already happening here. Something that I didn't mention here or in this drawing is also the questions that some of the people who are managing or building HPC high-performance computing machines are asking. Basically, they want to incorporate quantum processors into their infrastructure. And of course, very quickly arises the question to, well, what happens if I have several small quantum computers? Can I do more than just having them separately work in parallel to one another? Can I have them collaborate on some tasks and give me a bit more than just 3 copies of the same machines? And that's a question that you can only answer if you have quantum links between these machines. And so, of course, there are lots of challenges, and Tracy will talk about the hardware. I'll go over again with the software. But what is really unique in this kind of project is that unlike quantum computation, quantum networks and networks in general are asking us scientists to go to the application side much more than what is usually done for instance, for quantum computing. And the reason is that the business model of networks make them a bit further away from the private funding and the private companies. Because if you are building a quantum computer, you will be able to sell your quantum computer or your access to your quantum computer solely based on the performance of it. For networks, not only do you have to provide a very good network, but you also need to have already users for this network. The value of the network is both the quality of the network and the people already in the network. And this means that private companies have much more difficulty entering into this space, and the Quantum Internet Alliance is really tackling this challenge by putting a team of people working from the theory down to the really very applicable application side, trying to do all the work so that we get a functional blueprint for this kind of network, so that people can start really looking at it and saying, okay, I have a roadmap, and this is how these large-scale quantum computers can be built. So now I'll let Tracy describe a little bit more what the hardware challenges are.
Thanks, Harold. So we're going to start by taking a look at some examples of quantum hardware. And so here's the vision that we've already tried to outline for you, this idea of Europe, or in fact, the whole world connected by a quantum internet. And so what do we mean in particular by this vision? We're picturing quantum nodes. These are kind of what you see highlighted here in these little circles, where we would be able to carry out local quantum computation as well as quantum simulation and quantum sensing. And then these kind of lightning-like lines that are connecting those nodes, we want to, well, okay, we can see that those are channels in a network, that those are links in a network. And in this quantum network, that is to be able to distribute not only classical but quantum information that's encoded in quantum states, right, then we're going to have to face special requirements and requirements that are in fact much more challenging than communication over classical networks. So to look a little bit more carefully now at these components of quantum networks and quantum channels, we're going to refer to end nodes of a quantum network as kind of the parties in a network who would want to communicate. So I'm kind of pointing here with this arrow at one of these circles to say that we could imagine that might be one, okay, that's sort of in the neighborhood of where I am right now in Innsbruck, Austria. That might be one person who might want to communicate, say I want to, carry out a distributed computation with Harold, who's in Paris. And so at these end nodes, we would need to be able to process quantum information for our shared computation that was going to rely on the resource of entanglement. But in order to communicate with Harold, it's not going to be enough if we only have nodes at our individual sites and we have a channel, for example, a fiber optic cable that connects us. And that's because long distance channels are going to require quantum repeaters. And most likely those are going to be based on intermediate nodes intermediate quantum nodes with matter-based quantum states. So I'll come to that a little bit more a little bit later. So first I'm going to look at some examples of end nodes, and then I'll describe how we could realize quantum repeaters. So I want to comment first on the state of the art with these end nodes, and I want to give you two examples about connecting together two remote nodes over some distance. And so this first example is from Gerhard Rempe's group in Munich at the Max Planck Institute for Quantum Optics. And back in 2012, his group did a really pioneering experiment where they took two different atoms. Those atoms were coupled to optical cavities, and they were separated by about 20 meters. And they were able to establish that they could generate entanglement between those remote atoms. And this diagram, this sketch, is illustrating that was mediated by light that was sent between the remote systems. So this is one example of two rubidium atoms that are separated in space and that are each in their own vacuum chamber, but they can be linked via quantum entanglement. And the second example is from Ronald Hansen's group in Delft in the Netherlands, that was able to demonstrate a similar entanglement between nitrogen vacancy centers connected, in this case, over something like 1 kilometer. And so what's interesting to us in this consortium is to say, okay, given that the state of the art has been really about these achievements linking together two remote systems, how can we go beyond that, in particular scaling up to more nodes? So let me give you one example, and that's focusing on this example of nitrogen vacancy centers in diamond. And that's the example from Ronald Hansen's group that I showed you in the lower right-hand corner on the previous slide. And so you see a couple of different images here. Some of them are from the Hansen group at Delft. Another cartoon is from the Rachter group at the University of Stuttgart. Both of them are part of this collaboration. In the Hansen group, so actually, right, in both groups, this platform, nitrogen vacancy centers in diamond, you should think of that as, it's based on diamond defects. So these are, the nitrogen vacancy center is referring to the fact that one of these, diamond by itself would just be made up of these carbon atoms. But now you have at one particular location, you have a nitrogen atom and you also have a vacancy. And so we can call it a defect, but in fact, it's this defect that allows us to do quantum information processing. And so that information is going to be stored in that defect, in the electron spin of this nitrogen vacancy. And this is a solid state platform. It's inside of a cryostat, so cooled down to very low temperatures. Information can also be stored in the nuclear spin of a nearby carbon-13 atom. And so it's often the case in these experiments that researchers then map information from the communication qubit and store it in the memory qubit of the carbon-13 atom. And so I'm describing to you storing information in this solid state platform, but the key here for quantum networks is that these systems also emit light. They emit photons in the visible range, and in particular this light can be collected through the solid immersion lens that you can see in the upper left-hand corner that's been machined into this diamond substrate around a nitrogen vacancy center in order to collect those light photons efficiently. So this is a cartoon that's illustrating what was done in the past in the Hansen group, which is to establish remote entanglement between these two, between two of these different centers. So you can see again in this kind of image on the upper left, a photograph that's been kind of colored to illustrate that, and then also a cartoon on the right-hand side that's sort of illustrating the concept of linking together the remote systems. So on the cartoon on the right-hand side, what we're looking at, we see these different yellow and purple balls, each with an arrow, and those are indicating the storage of information in these matter-based qubits or quantum bits. So we're storing information in this defect in the electronic structure, and the arrow is indicating that we're encoding information in what we would refer to as spin up or spin down, that we're saying that it could be, we're encoding it in some direction of this electronic state, or that we're associating with the electronic state. Okay, and so we see three of them, and that's indicating that these purple ones are this, where the information is stored in the nitrogen vacancy center, and then the yellow one is indicating this, this carbon-13 memory qubit. And so in this cartoon, in the first diagram on the top, what you see is that a photon of light, a single quantum of light, is emitted from the nitrogen vacancy center on either side, and this little squiggle is kind of indicating the motion of that light onto a piece of glass that splits the direction. And so it could actually go from either one of these nitrogen vacancy centers to either one of those little detectors, those little gray cubes. And in fact, it happens with very low probability that a photon is emitted. So only one of those detectors clicks, or here in the picture it sort of shines green. And that detection event means that one, but not two, of those nitrogen vacancy centers emitted a photon, but we don't know which one because we lost the ability to distinguish between which emitter sent which photon using that piece of glass, that beam splitter. And so through this detection event, the two emitters become entangled with each other, and that's illustrated through this purple squiggly line. So what I want to sort of mention now is the most recent result from Ronald Hansen's group at Delft, which has now taken this entanglement between two remote systems, and Hansen and his team have recently been able to link together three systems. And so this is what's illustrated in this cartoon here. And you see again this purple spin being used, so this kind of sphere with a little arrow being used to indicate when it's a communication qubit in purple, and then when it's being stored instead in the carbon-13, that's this memory qubit in orange. And so in this case now there's three separate systems, two of them below in this first lab that are separated by just a couple of meters, and the third in a second lab that's 30 meters distant. And so his group was able to establish actually entanglement that was shared between all three of these different quantum emitters. And they mediated it through that memory qubit. That is, entanglement was first established between one pair of the purple spins, the purple nitrogen vacancy centers, and then it was sort of transferred onto this memory qubit for storage, so that entanglement could be established then between a new pair, and then together it could be kind of linked to create to establish a quantum link across all three of these systems. So I want to sort of, this is quite superficial because I'm just trying to give you an overview of the different physical platforms that are being used here. So I'm going to now shift gears and mention the second platform, which is also one of the ones I showed you in kind of giving you a sense of the state of the art. And so I mentioned before that this was from the Rempe group in Munich. And this is a group where they're confining atoms in optical traps under ultra-high vacuum. And so information, just like in the nitrogen vacancy center where information is being stored in electronic states, here quantum states are also being stored in electronic states. And in these cases, it's the electronic states of the atom. And then what you also see in this illustration is the so-called optical cavity. And those are these two mirrors that are facing one another. So in the diagram on the upper left, you see two different mirrors, and there's an atom in between the two of them. And because light bounces back and forth between the mirrors, then the optical cavity can serve as a trap for photons for these light quanta. And that allows a single photon to interact strongly with a single atom. And so I just wanted to highlight a recent result from that group where they're still looking at two systems, as I showed you in the earlier slide, where they're able to establish an elementary network between two remote systems. But something that this group is interested in exploring is different ways of, novel ways of establishing an entanglement between two remote atoms. And so in this case, instead of using an approach like the one I've described to you for nitrogen vacancy centers, instead of each system generating a light particle and having those particles impinge on this piece of glass, this beam splitter that erases information about where those particles came from. Instead, this is an approach which you can see in the using the laser pointer here in this diagram in the middle on the right-hand side. So there's actually a light particle that comes from above and is reflected off of the optical cavity that holds the first atom. And it sort of interacts or doesn't interact with that atom, then it bounces back off, it goes down and is reflected off the second cavity. So either it interacts or it doesn't with this atom. And in the end, that light particle, or actually what we would refer to as a coherent state of light, that light signal is then detected. And that information, that process of reflecting the light off of these two systems is able to achieve a logical operation between the two remote atoms. The upper right-hand corner is just a way to characterize that logical operation between two remote atomic systems. The final platform that I wanted to mention today for these end nodes, for these nodes at places in a quantum network where you can carry out quantum information operations, where you can manipulate these quantum states. This is a platform that we're using here in my research group at the University of Innsbruck, and also in the research group led by my colleague, Benjamin Lanian. So in both of our groups, you might notice that these bullet points that I've written here are quite similar to those for the atomic system. So here, instead of neutral atoms, we're using ions, in this case, singly ionized atoms. And these, because they are charged particles, we can confine them in electromagnetic traps. Just like the atoms, we can find them under ultra-high vacuum. So we don't need to put them in a cryostat like the nitrogen vacancy centers. We can work with them at room temperature, but we do need very, very low vacuum conditions. We encode information in the electronic states of the ion, just like for the atoms. And again here, what we're using is this optical cavity to trap the photons, to trap the light particles that are interacting with the atomic systems. So just to kind of give you an overview of what we're working on, we've been working on establishing remote entanglement, similar to the two experiments that I've shown you previously, between two laboratories in different buildings. You can see them illustrated here. So these are two different systems in which we trap atoms. These ionized atoms, in this case, these are calcium ions, and we couple them to an optical cavity, and we're able to entangle each of the atoms with a single photon. That's what's shown actually in the data here. This is data that's based on a measurement that one can use to characterize this entangled state between a single photon of light and a single atom. And so this verifies that we have atom-photon entanglement. We do that at each of the two systems. And then similarly to the nitrogen vacancy experiment I showed you, you can send those photons to an intermediate location. So this is, again, actually, these are experiments that are going on today, even as we speak, trying to connect together these two labs and then establish a quantum state that's shared across the two particles, that is, that's distributed over this distance. Okay, so I hope that I've given you sort of a sense about these different end nodes and the kind of physical platforms that can be used and that are being used in different labs. I've shown you ones in Europe as part of this Quantum Internet Alliance, but of course this is research that's going on in many different labs worldwide. And so now I want to turn to the second aspect of hardware that I told you about at the beginning, and this is about quantum repeaters. And that's the question of how we can address the limits of having long links, on the scale of maybe several hundreds of kilometers that might be interesting. And we know that doing that over optical fiber directly is a serious problem. The reason it's a serious problem is because loss in optical fibers is exponential with the fiber length. So fibers have very low loss, but still the longer you make them, the worse it gets. And so in particular in this example, if you have a 10 gigahertz source where you're making a single quantum of light, a single photon, at a 10 gigahertz rate. So at the very beginning, at the source, you're just sending out one photon and you can get that every 1/10 of a nanosecond. But now if we look at how that propagates in a fiber, that means that if you're 500 kilometers away, then it's going to take you, you're only going to get one of those photons every second. And if you're 1,000 kilometers away, it's going to take you more than 300 years. So that's where, it maybe feels to us with our intuition that 500 kilometers is like 1,000 kilometers, but you can see here it's really not. So things start to get very bad very quickly on this scale of hundreds of kilometers. And that's where these ideas about having quantum repeaters come in. So, right, we should remember, okay, what's happening in the classical world. Certainly we're able to send information like this webcast all the time over, over the globe without even worrying about it. So in the classical signals, in a classical network, you can amplify signals, but unlike classical signals, these quantum states of light are not something that we can amplify and still preserve the quantum information that they're encoding. So on the right-hand side here, what I've sketched is a cartoon of this kind of a quantum repeater, or the building blocks for a quantum repeater. So again, you see these ideas about little, in this case, little spin states where we can encode information. So you can think of these red dots as one of the kinds of systems I've shown you previously of nitrogen vacancy centers or atoms or ions, where we can store information, but also generate light particles. So little squiggles are the light particles. And so in this picture, this is a picture where you can picture each dot, each atom, say, generating a photon. The photons impinge on this piece of glass, this beam splitter, and that allows us to entangle a single pair. We do it again here with the second pair. And now we have two pairs of entangled atoms. And then we can do a measurement on a central pair of atoms here in this diagram. And this is going to succeed in entangling actually the two outer atoms. So it's a trick that you can use to essentially transfer the entanglement, so as entanglement swapping for that reason, to the outermost atoms. So what did all this entanglement bring us? The point is that now the relevant distance for photon loss in this cartoon is actually half the distance between the two outer atoms. And so as I've argued, right, 1,000 kilometers can be very, very different from 500. Half can be a very big deal when you're talking about exponential loss. And of course, you don't just need to split the system in half. So you could continue to keep splitting a quantum repeater down into smaller and smaller pieces and concatenate this kind of approach of a so-called entanglement swapping operation. So this is, again, I've described to you entanglement swapping, and what we've seen is that it requires the fact that you can generate entanglement between remote systems. And I've written here that it needs to be heralded. That means you have to know when it worked. And in this case, we know when it worked when we detect the light particles that generated it. The problem is that this detection, this knowing when it worked, this process of heralding entanglement creation, that is going to limit the repetition rate. And so when people look at the best kind of quantum systems for these kind of repeaters, they're interested in multiplexing. That is, ideas where you can, or situations where you could store multiple quantum states in parallel, for example, at different frequencies or spatially. And so let me just show you two examples. One is in the Deriedmatten group in Spain at ICFO. And so this is a group using rare earth doped crystals. And so in this case, you could store information actually in many, so store quantum information, not just in a single atom or ion or nitrogen vacancy centers, I showed you before, but actually in many different modes simultaneously, many different quantum states in parallel. And you could also do that in an atomic ensemble, as in this picture from Julien Leroth's group in Sorbonne, at the Sorbonne in Paris. So those are two examples of how you could use different kinds of quantum systems that might be more suited for these quantum repeater architectures. The final example I want to mention is that there are also approaches to these quantum repeaters that don't require quantum memories, that is, that don't require storing information in a matter-based platform. And so here's an example from Peter Lodell's group in Copenhagen, where they're actually trying to use trains of photons, trains of light pulses that come out of a quantum dot as the basis for a quantum repeater that would, again, let us avoid this distance scaling problem. So I know I showed you a lot of different things. That was kind of the point. So this was going to have to be superficial. We couldn't get into in depth on any of the platforms. But what I wanted to communicate here is that there's a wide variety of physical platforms that are being investigated for these end nodes and also for quantum repeaters. And that in many groups worldwide, people are focusing on increasing the complexity, the number of nodes in these networks, which are really just elementary networks as part of basic research already at this stage. People are also very interested in these ideas about multiplexing, that is having storage in memories across different, using different frequencies or different spatial locations as a route to speed up long distance quantum communication. And so then with that, I will turn things back to Harold, who's going to take us from hardware further up the quantum stack.
Thanks, Tracy. Yeah, so I think from my perspective, if I want to summarize all what was presented on the hardware before, I would say, look, there are a lot of options. And maybe I don't manage to get to the next slide. Okay, yeah, there are many different options, but what is very important here is that you have to take into account these different options and the fact that when you build your network, you'll have something very specific to keep in mind, is that at one point in time, maybe you'll have some homogeneous principles that make it working within your network, but maybe you are going to try to connect your network to another network with different kinds of devices. And basically, if you want this to be useful, you need these two networks to be able to work together. So you'll have to have this extendability in time, in space, sorry, but also in time, because you know that a network is a decentralized object, infrastructure, and some of the nodes will want to be upgraded at one point and to improve the efficiency. So these nodes, when you change the hardware there, you will have to maintain the compatibility with the rest of the network. So this extendability is really a constraint that is very unique to networks. It's also the same in the classical networks, but you have to take it into account in the quantum space as well. And this is very different from, for instance, from people trying to build quantum computers. Quantum computers, you have a single machine, and it has to work at a given within a given environment, and you know very well this environment and you control it. Here in a network, things are much more complicated because it can change in time and in space. So the very first thing that you have to take into account is this variety of devices and have what I call functionality abstraction. One way to basically put down all the working principles of your network, layer by layer, a little bit like you have in the classical setting. so that within each layer you can design protocols that will give you this functionality and that will abstract away all the hardware that Tracy has been presenting. So this work was done partly or mainly at Delft, defining this network stack from the physical layer, basically what Tracy was mentioning before, and then trying to get to the link layer, which is generating this entanglement in a robust fashion. Network layer starts sharing this entanglement with the repeaters, and then the transport is really like managing a way to basically teleport using this entanglement, teleport the quantum information you want from place A to place B in time and in cooperation with the application that you want to perform. So each of these layers, they have protocols that are designed specifically for this, and all what we have been doing in the Quantum Internet Alliance is really based on this principle of entanglement sharing. So it's various degrees of entanglement sharing in the network. I don't know. Yeah, okay. I'm back on track. But then, of course, like having a protocol is not enough. You want to control the devices, and you need to take into account the various limitations of these devices and get the software, a software API, if you want, to control the devices and be able to communicate with one another. So there is the quantum communication, but for controlling all this, you definitely also need to have classical communication and synchronization between the various hardwares, or signaling, so that as Tracy was mentioning, you need to know that your entanglement generation is heralded, but this heralding thing needs to be, the signal needs to be broadcasted to the network, so that you can use it. And even at a larger scale, the question might be, you want to book a resource, an entanglement resource between two remote links, and the question in there is, how do you do this? How you manage the global state of the network? So there are various scales of control that you need to implement and think about and make it coherent, so that again this extendability is preserved at all costs, I would say. So once you have defined this, then you can actually start building a software stack. And there the real challenge is to try to have, as soon as possible, platform and hardware independence. Why do you want to have a hardware independence? Is because as you go up in the stack, you basically don't want to have to know where each device and what technology each device on the network is running on. You just want to have some, let's say, abstract definition of these devices. What are their characteristics? But that's it. You know, you want to know that maybe this quantum memory is working at this with these characteristics, that this quantum repeater is able to do this and that. This source is firing at this rate. But that's basically it. So you want to have this abstraction, so that later on, and then definitely at the application side, someone can go and code an application for the network without knowing exactly how the network is being done. Otherwise, it's definitely not anymore a network. It's a sort of distributed quantum device. But you have lost then all possibility to connect and to evolve your network in a decentralized way. So that's really something very, very important here. Yeah, maybe Tracy, if you can go one slide further. Yeah, thanks. But then once you are at the application layer, you need to design new protocols and protocols now for doing something useful with the network. So now you are with the stack, you have been able to distribute entanglement, to route qubits from point A to point B across your network. But then what do you do with it? And there are a whole lot of applications already that have been published by lots of people and gathered by some of the members of the consortium, mainly in Sorbonne University. Under the form of a protocol zoo, like we have a complexity zoo and an algorithm zoo. Here we have a zoo for quantum protocols. But what is more important than just having the collection of the protocols is analyzing these protocols. In fact, we think that the first networks will probably be simpler than just a full-scale network, and this is quite, understandable. It's difficult to build these networks, so they will progress through various stages of capabilities. The first capabilities will be probably something called prepare and measure. Then we'll go onto the entanglement generation, which is what Tracy talked about most. And then we will have memories at the various repeater nodes. Having this ability to store, even for a short time, some quantum states is really something that enables and opens up the possibilities in terms of applications. So what we wanted to do was to take all these protocols, analyze them, and basically decompose these protocols into subroutines and usage of resources or elementary resources. So how many qubits do you send from point A to point B? What kind of entanglement you need? Do you need memory? Do you need to apply small quantum computations locally? And once you have done this, organized this, then you can start really having a global picture of what you can do at a given network stage. And this is very important because all the time what we have to do is take these protocols, of course design new protocols, but we need to design protocols that we can run. And designing protocols that we can run means we need to optimize everything. So there are two kinds of optimizations. There is a qualitative optimization, basically trying to get from, let's say, a network stage where you need quantum memory to a network stage where you would only need entanglement generation. That's really a huge step, because if you don't have quantum memories, then you can still perform your protocol. But more than this, you might have entanglement generation, but you might not be robust enough in your protocol to losses that could still occur, or to a certain rate of entanglement generation. So what you want also is to really optimize the resources quantitatively. And this is another step. Basically, you need to count all the qubits that you are using and trying to save as much as you can. Because let's say if you have 10 or 20 qubits at a node, well, if your operation for doing something interesting is requiring 30 qubits, then, well, you can't do it. But if it's 19, then suddenly it becomes possible. So this is something that usually people doing protocols are not accustomed to do. We always have this vision of complexity theory and things like this, like counting asymptotic resources. And we are very happy when we have lower asymptotic resources. But the problem is, and that's the difference and the interest of this Quantum Internet Alliance, is that sometimes you have to go back to Earth and really count the resources one by one and saying, okay, this works and this unfortunately doesn't work yet. But we'll now work on to making it happen either by further optimizing or trying to improve the hardware. So this optimization is very important. And on the next subject that we have here, on the next slide, it's actually the simulation. The simulation is something that you very, very quickly get into when you look at networks. And it is extremely complicated subject. You need this because basically there are too many parameters to look after. There is the topology of the network. There is all these parameter space that you can want to explore. And sometimes you are lucky enough that you have some analytic behavior that you can that you can derive, but most of the time you have nothing. So you have to capture the behavior of your network on a larger scale or global scale. That's very important. And especially if you want to assess the performance of your devices with respect to a given application. Applications, and mostly applications that are providing security, require some capabilities from the network. Some quality of entanglement and some quality of operation applications to your quantum states. And the question is like, how do you ensure that your network is really providing this, or how do you anticipate your network is providing these kind of things? And you can only do that through simulation. And there has been a software package called NetSquid, developed by the Quantum Internet Alliance, which is providing this. And just to give you a very short glimpse at how complicated that is, basically, each of the node is a quantum computer. So you need to simulate a small quantum computer locally, and then you need to take into account everything that makes it a network. So you need to have the interactions between the nodes. You have to take into account the topology, the asynchronicity between the various processes, the fact that the number of qubits is evolving all the time. It's not like in a processor where you know that you have whatever, like 30 qubits that you want to simulate. Well, we constantly in the network create new qubits, destroy qubits, so the number of qubits is varying all the time, and this is a challenge just by itself. So these simulation tools are extremely important. We have first versions of these tools. They are already very useful, but a lot remains to be done there to basically integrate smaller simulations into a global behavior, because if you are simulating really the full stack from the physical layer to the application side, well, it's a lot of code and it's a lot of computation, and we know that it is inefficient in the end. Otherwise, we wouldn't be using the quantum internet. But we still need to have a glimpse of how things behave, and simulation is really helpful on anticipating how we should build the device and put the repeaters with one another. And the last thing that I wanted to talk about is all the certification and verification questions that you need to address in a network. Again, here, referring to the difference between a quantum computer, you have potentially malicious players all over your network. Some of the nodes might be corrupted. Some people might try to put some devices on the network that are not delivering the service they were supposed to deliver. So you need various levels of how to say, like property discovering and certification of the devices, even going to the more adversarial scenario of verification. So certification is mostly looking at hardware functionalities or performance or even resources, and testing that it works and that it's really providing you the service before you put the device or the functionality in operation. Okay, so you test it before, it works okay, you agree to put it in there, and then you are happy because you think it will deliver the service it was advertising in the first place. But then the problem with this kind of strategy is it doesn't prevent the devices to deviate later on in the process of being used. And there you have to resort to verification. And verification is really something that is being performed while the resources or the computations are being performed. And you can certify resource, you can verify, computations or distributed tasks. But there again, you have to keep in mind that the most important thing, besides security, is that you need to be able to compute something. If you are using all your resources to just have security, you cannot compute or you cannot distribute tasks anymore. So you have to have this balance between overhead due to security and still resources to do the interesting stuff. And basically, you have to manage to get rid of all overhead, basically, maybe besides some repetition. And that's the kind of stuff that we are doing at Sorbonne University, trying to bring down the resources as low as possible. So that concludes what I wanted to say on the challenges for the software part. And as a conclusion for the seminar, basically what we want to do with the Quantum Internet Alliance is give entanglement for everyone from anywhere on Earth, because that's only with this kind of capabilities that we will unlock the impact, the real impact of the quantum technologies. And I thank you for your attention, and I think we'll answer questions now.
Wonderful. Thank you so much, Tracy and Harold. We'll take a look at the questions that have been coming in. So first from Jasmine, why do we need both entanglement and optical fiber connection? Won't entanglement be enough?
So maybe I can quickly answer it that if we could generate entanglement at any two distant points, then we wouldn't need an optical fiber connection necessarily. But it's often the case that we need the fiber connection in order to generate remote entanglement. You can certainly imagine generating entanglement locally and then taking those two halves of entanglement and kind of transporting them to distant locations with a car or a train or a plane, but that's going to take a long time and you'll probably lose that entanglement in the meantime. So the general approach is to take advantage of optical fibers in order to generate remote entanglement.
Great, thank you. Calvin asks, will this technology be used between deep space satellites and Earth-based communication systems that send messages back and forth instantaneously?
Well, I'll try to answer, even though it has a hardware part in it. So there are projects within the Quantum Flagship that try to tackle this question of having entanglement between satellites and Earth stations, and definitely having the possibility to go through satellites to broadcast entanglement or share entanglement, so that we extend or have another way of extending the networks is an interesting and definitely something that is being explored by research groups. The only remark that I want to make as well is that it's not instantaneous communication. Unfortunately, we cannot do this. Having entanglement just gives you the possibility to send the qubits, but to send the qubits, you will have to also send classical information through whatever means you want. It could be open air or fiber, but you need to also send this classical information to get the quantum information at your destination, and this takes time as well. So no instantaneous communication, but we'd be happy to already have space entanglement, I would say.
Great, thank you. Is it possible to connect the quantum computers with different technologies or only the same ones? Shaida wasn't sure she's understood properly there.
Yeah, so I can take that. Yeah, because that's something that I didn't address in the hardware part. I talked about connecting, say, one nitrogen vacancy center to another nitrogen vacancy center, or one ion to another ion. But you could ask, well, what if I want to connect an ion to a nitrogen vacancy center? And that's certainly something that people are very excited about and interested in. And there have been some experiments connecting or working in that direction of hybrid systems. And the key aspect is that you need the frequencies of light that interact with those systems to match one another. And so you could do that two ways. Either you could find two different quantum systems that happen to be interacting with light of the same frequency, or you can convert that frequency. So using nonlinear crystals, using methods that are well known, what wasn't immediately clear was that whether that would preserve the quantum information, but what's been shown in recent years is that that can be done with low enough noise to preserve quantum information. So yes, you can actually convert between different frequencies in order to link different kinds of systems together.
Great, thank you. What is multiplexed quantum memory?
Yeah, maybe just to briefly, because I talked about it, but maybe not fully. So when I showed, for example, a cloud of atoms, that would be the idea that actually you can store information at different physical spaces in that cloud, or so that instead of, because you have so many different atoms, you actually can store in, you can have, in that case, kind of spatially distributed storage throughout that cloud. That would be an example.
Great, thank you. What adaptation, so I'm trying to translate this question. What adaptation different layers of the internet, i.e. the application layer, physical layer, has to make to accommodate the underlying changes of quantum effects? So I'm trying to scroll down. In terms of data exchange, or a completely new layer is getting introduced below a physical layer, a quantum layer for the data conversion. I might not have understood that question quite right.
Yeah, but it's okay. I think I'll try to answer to this. Well, I think the question is the following: is asking like, well, imagine that I have a classical internet. Can I use the classical internet to convey quantum information, or do I need to change the layers? And yeah, you have to change the layer completely. I mean, you have to build a physically different network. You need to have new fibers and have, you know, like, yeah, separated channels, communication channels, so that they don't interfere with the classical data, because otherwise it would be complicated. And of course you need to rebuild everything from scratch, at least on the network layers. As I've shown, like, it was one of the challenges of the project. You need to restart from scratch. And the principles as well are completely different. As we try to say it with Tracy, in fact, the question is not really sending quantum information. The question is more like distributing entanglement, having this entanglement ready for when you need to send the quantum information. And this is a fundamentally different way of doing things. And unfortunately, it's a different way because as Tracy was saying, if you try to send your information directly into the fiber, you lose it. Or if you just do it on very short distance, that's fine. But since you cannot amplify it, then you are stuck. But with entanglement doesn't contain any information. It's just a resource. So if, you know, very few entanglement arrive at the other end of the network alive, then that's no problem, because you haven't lost anything in there. You just have very few pairs of entanglement, but you can still use them to transmit faithfully your quantum information. So completely different principles, completely different stack, and different hardware. So it's new.
Thanks very much. We've got time for a couple more questions. So let's just have a quick look at what else is coming. How long will it be until we have a quantum internet?
So maybe to try to answer that, it's a very complicated question, but maybe the best answer is that that this stack that maybe I'll go back actually here in the slides. Harold showed on the right-hand side these stages of a quantum network, and so I think we can expect that, okay, if we define a quantum internet as getting to the top of this list of stages where we can do everything we envision, that's going to be more than 10 years. And yeah, how much more we could take a lot of guesses about that. But the exciting thing I think for us is that we expect that actually along the way there's a lot of interesting quantum network protocols that we'll already be able to achieve. as we work our way up through these kind of list of different functionalities that you're seeing here in blue. But I think that, right, realistically, until we're able to take advantage of entanglement between any pairs, between nodes on long distances and do really sophisticated things, you know, this is more than a decade.
Wonderful. I think that's all we've got time for today. Sadly, we've run short on time. If your question hasn't been answered, there are a few we haven't managed to get through, so sorry about that, but you will receive a reply by email. If you would like to watch this webinar back again or recommend it to a colleague, it will be available shortly on physicsworld.com. Just click on the audio and video tab and go to webinars. There's still time to register for our last presentation running this week, A Quantum Future of Computing, which is taking place tomorrow. So thank you for dialing in today, and I hope we'll see you at our final session tomorrow or in the future Physics World webinar. So on behalf of our sponsors and our presenters today, thank you very much for joining us. Enjoy the rest of your days, and we'll call this the end of the webinar. Goodbye for now.